Welcome back to Calculus 3. I'm Dr. Jeff Groh. Today we're going to talk about partial derivatives. When you have a function of two variables, how do you define the derivative? Well, how did we define the derivative way back in Calculus 1? In Calculus 1, we defined the derivative to be the limit as h goes to 0 of f of x plus h minus f of x all over h. This gave us the difference between two close y values, and the denominator is the difference between these x values. So it's a delta y over a delta x, and the limit as delta x goes to 0. We get the slope of a tangent line to the curve. Now, we can do something similar here. We just need to think about what it means. Let f be a function involving two variables, by which we mean that f maps some domain in R2 into R. The partial derivative of f with respect to x is denoted by, each new operation gets its own notation. We need to be particularly careful about this one, and there is more than one notation. There's, first of all, df dx. Yes, this is the old style partial, old style d that I showed you in the last lecture. This is the way d's were written before the Civil War. So one notation for the partial derivative of f with respect to x is with this very stylized bent d. Not a flat d, but this little old style bent d. Also, it's denoted by a subscript. Just a subscript on the variable. If you write f with a subscript of x, that means you perform an operation on that function, the partial derivative with respect to x. It can also be expressed as dx f. Now, how is it defined? The good news is it's defined in a way very much analogous to that in Calculus 1. We'll take the limit as h goes to 0, f of x plus h, comma y minus f of x, comma y divided by h. Can you see what we're doing here? In this definition, we're finding a slope in the x-axis direction. We're changing x a little bit. So if we had a surface like this, as we move parallel to the x-axis in the domain, holding y fixed, we'll get slopes of little tangent lines as we march parallel to the x-axis. And so that's what the partial derivative with respect to x gives us. Not tangent lines in any direction, but as we march parallel to the x-axis. You can see that partial derivatives with respect to y will give you slopes of tangent lines as you march parallel to the y-axis. Obviously then, df dy will be the limit as h goes to 0 of f of x comma y plus h minus f of x comma y over h. Note, in this particular derivative, we're treating x as though it is fixed. It is not changing. We treat x as though it's constant when we're taking the derivative with respect to y. Similarly, if we take the derivative with respect to x, we treat y as though it is constant. So let me give you some examples. Let's suppose that z is the function, let's say 3x squared y plus 5x cubed y squared plus x plus 7y. When we take the derivative with respect to x, we treat y as though it's constant. So we get 6xy. Y is coming along just like constant factors do. Plus 15x squared y squared plus 1. The derivative of x with respect to x is 1, and then the derivative of 7y with respect to x is 0 because we are treating y as though it is constant. Then dz dy is 3x squared. The derivative of y with respect to y is 1. The 3x squared comes along as a constant factor. Then we get plus 10x cubed y plus 0, and then plus 7. In our next example, let's suppose that our function is x plus y over x minus y. To calculate fx, the derivative with respect to x, the partial derivative, we need to use the quotient rule. We do the derivative of the top with respect to x. Y is being held constant. The derivative of the numerator with respect to x is 1 times the bottom minus the top times the derivative of the bottom with respect to x, and that is 1, divided by the bottom squared. This simplifies. You can see that we'll have x minus x. The x's go away. We'll have a minus y, that's minus 2y, over x minus y quantity squared. Similarly, let's calculate the partial derivative of f with respect to y. Again, we apply the quotient rule. The derivative of the top with respect to y is 1 times the bottom minus the top times the derivative of the bottom, which is minus 1. We're taking the derivative with respect to y. The derivative of x with respect to y is 0. The derivative of y is, of course, 1. We get minus 1, divided by the bottom squared. Simplifying, we get x minus negative x. That gives you 2x, and the y's cancel. What if I give you something like f of x comma y is the inverse tangent of x squared y? You know that the derivative of the inverse tangent of x is 1 over 1 plus x squared. That's the one I asked you to memorize. So let's calculate the partial derivative with respect to x. This is going to involve the chain rule. The derivative of arctan is 1 over 1 plus quantity squared. But you must multiply by the derivative of the inside with respect to x, so you hold y constant. So we get 2xy over 1 plus x to the 4th y squared. Now let's do the partial derivative with respect to y. Again, 1 over 1 plus x squared y quantity squared times the derivative of the inside, which is merely x squared. In our next example, I want to calculate higher order derivatives. In particular, if I write fxy, that means do the derivatives in the following order. Do the derivative with respect to y last, but the derivative with respect to x first. you can see how the Leibnizian notation puts things in the reverse order of this Newtonian notation. Also, fyx then would be take the derivative with respect to y first, and then with respect to x. Kind of the reverse of the order presented here. Do the one closest to the f first, and then the next. In this one, you work from right to left. In the present case, let's suppose that we have something like 5x squared y cubed plus 7x y plus 2. Let's calculate fx. That's going to be 10xy cubed plus 7y. Also, fy, that's going to be 15x squared y squared plus 7x. Now, let's calculate fxx. That means two derivatives with respect to x. That'll give us 10y cubed. Fyy is 30x squared y. Now, let's calculate fxy, the derivative of x with respect to y. That gives us 30xy squared plus 7. Let's calculate fyx, the derivative of fy with respect to x. That's going to be 30xy squared plus 7. The natural question that should leap into your brains is it always true that fxy is fyx? The answer is almost. This equation will hold for nice functions, but for other situations, maybe it won't. In fact, we will give an example where this does not hold. We call fxy and fyx mixed second order partials, or mixed second order partial derivatives. We need a theorem that tells us what is that class of well-behaved functions that do what they're supposed to do and have mixed second order partials equal to one another. This is called Clairaut's theorem. If fx and fy are continuous on an open set containing some point x naught. So it's interesting that the topology of the set is important. It can't be a closed set. It has to be a set that's fat, a set that contains these little open balls. You can stuff it full of grapes. Containing x naught and fxy and fyx are continuous at x naught. So they exist and are continuous at this point. So the mixed second order partials don't need to be continuous on an open set, just at that point. The first order partials have to be continuous in an entire open set containing that point, i.e. a neighborhood. Then fxy evaluated at that point x naught will be equal to fyx at that point. So you get equality of mixed second order partials, but the functions have to be well behaved. Well behaved so that the first order partials are continuous on an open set, a neighborhood of the point x naught. And the mixed second order partials are continuous. They exist and are continuous at the point x0. Now I want to give you a very important example where these second order partials don't equal each other. Let's suppose the function has the form xy times x squared minus y squared over x squared plus y squared, as long as xy is not the origin, and 0 at the origin. Now, I claim that the mixed second order partials at the origin are not equal. This doesn't violate Clairaut's theorem for reasons that we will give shortly. First, I claim f is continuous at the origin. Let's see if we can prove that. First, note that 0 is less than or equal to the absolute value of xy, x squared minus y squared over x squared plus y squared, and that is less than or equal to the absolute value of xy times x squared plus y squared over x squared plus y squared. If you make the minus into a plus, you have to get something bigger. This is 1, and so we just get the absolute value of xy. If we take the limit and use the squeeze theorem, the limit as x goes to the origin of this absolute value of the function, if both x and y are going to 0, we will get 0. So by the squeeze theorem, the limit of the function off of the origin will be the same as the function value at the origin, in the limit as x goes to the origin. Since the limit value equals the function value, we deduce that f is continuous at the origin. Let's look at the partial derivative at x when x is not at the origin. We'll have to calculate the derivative with respect to x at the origin as well. Note that we can distribute to obtain f is x cubed y minus xy cubed over x squared plus y squared and calculate the derivative directly using the quotient rule. The derivative with respect to x will have 3 x squared y minus y cubed times the bottom minus the top. That's going to be x cubed y minus xy cubed times the derivative of the bottom with respect to x, which is 2x, divided by the bottom squared. How does this simplify? You can see that we can take a y out of both of the terms in the numerator. It's usually best to factor first if you can. And then we'll simplify. You can see that we'll have a 3x to the fourth minus a 2x to the fourth gives you x to the fourth. We have a minus y to the fourth. Then we have a 3x squared y squared minus x squared y squared is 2x squared y squared. And then minus minus another 2x squared y squared, so that's plus 4x squared y squared. And then That counts for all of the terms in the numerator. All right, over here, fx is y times x to the fourth minus y to the fourth plus 4 x squared y squared over x squared plus y squared quantity squared. Similarly, you can show that fy is x times x to the fourth minus y to the fourth minus 4x squared y squared over x squared plus y squared quantity squared. So we have the partial derivatives as long as x is not at the origin. Question is, what happens at the origin? We have to resort to the definition. That's the limit as h goes to 0. F of 0 plus h comma 0 minus f of 0, 0 over h. The function value at the origin is 0. The question is, what happens when y is 0 and x is equal to h, not equal to 0? Well, either way, you're going to get 0. Similarly, the partial derivative of f with respect to y at the origin is also 0. Now, I want to calculate fxy at the origin, and we're going to use the definition of the partial derivative with respect to y. That's going to be the limit as h goes to 0 of fx of 0, 0 plus h minus fx of 0 all over h. We're perturbing the y-coordinate a little bit on fx and then taking the limit. We already know that the partial derivative of f with respect to x at the origin is 0. So we're taking the limit as h goes to 0. We have this 1 over h times fx evaluated at x equals 0, y equals h. So we're going to have an h, 0 minus h to the fourth, plus 0, all over 0 plus h squared squared. That's h to the fourth. If you do the cancellation, you'll see we get minus 1. Next, let's calculate fyx at the origin. If Clairaut's theorem applies in this case, we should get -1, just like before. Does Clairaut's theorem really apply? Let's find out. This should be fy at 0 plus h comma 0 minus fy at the origin, which we know to be 0, all over h. That's the limit as h goes to 0. We still have this 1 over h. Fy evaluated when y is 0 and x is h. X is h. We'll have h to the fourth minus 0 minus 0. And here we have h squared squared. That's h to the fourth because y is 0. The limit is obviously positive 1 now. So the mixed second order partials are not equal. This is a very simple rational function except at the origin where we've patched a hole to make it continuous. And yet the mixed second order partials are not equal. So what is going on here? It is possible to see that the first order partials are continuous in a neighborhood of the origin. It's the mixed second order partials that must not be continuous at the origin. I ran into a problem that directly relates to Clairaut's theorem with respect to shockwave solutions to the Einstein equations. The Einstein equations are the curvature of space-time is directly proportional to the mass-energy momentum tensor of space-time. If you have fluid shock waves, that means t will have discontinuities in it. G involves the second-order partial derivatives of the space-time metric. Those may or may not be interchangeable, especially because you're expecting those second-order partial derivatives to be discontinuous, because t has jump discontinuities, shock waves. I'd like to talk about the tangent plane. In the context of surfaces of the form z is a function of x and y. Suppose I have some domain down here, and some surface results above that. I'm going to draw a little big, because I want to look at the tangent plane at some point. In order to define a tangent plane, I need a point on that surface, and I need the normal vector, because the equation of the plane is 0 equals n dot x minus x naught. I'm going to create a function. The function is going to be capital Phi. It will depend upon x and y. And it's going to be x comma y comma f of x comma y. Now, suppose I hold y fixed and allow x to be a variable. If I let x roam around, then what I end up with is a curve on the surface. If I take the derivative with respect to that parameter x, I get a tangent vector, 1, 0, fx at xy. This ends up being a tangent vector to the surface. Since it's tangent to the surface at this point, it will be a tangent, it will lie in the tangent plane. Similarly, if we hold x fixed, then we'll get a tangent vector in another direction when we hold x fixed and take the derivative with respect to y. We get two tangent vectors to the surface at a particular point. To find the normal vector, all we have to do is take the cross product. Since these are nicely stacked, it makes the cross product easy to calculate. We'll get 0 minus fx. I'll suppress the functional dependence on x and y now. I get fy, but don't forget to put a minus on that middle cofactor. And then 1. And so, since the z-coordinate is positive, it will be pointing up in the upper, towards the upper half space from this point. We're going to evaluate this at this point, at some point x naught, y naught in the domain. Remember the equation of the tangent plane is in this form. We have minus fx. For the moment, I'll suppress the functional dependence on x and y and the evaluation at the point x naught, y naught. Minus fy, and then positive 1. We're dotting that with x minus x naught, y minus y naught, and z minus z naught. This gives us minus fx. I'll write this at x naught times x minus x naught, minus fy at x naught times y minus y naught, plus z minus z naught. Now I'm going to move a lot of these terms around. I'm going to move some terms to the other side of the equation. I'm even going to move this z naught. I'll have z, which is f of x comma y, equals z naught, which is f of x naught. These become plus fx at x naught times x minus x naught plus fy at x naught times y minus y. I have then the equation for the tangent plane, which is a local approximation, a linear approximation to the function itself. You can see that the function will be close to the tangent plane as long as you don't stray too far from that point. If the surface goes like this and the tangent plane is like this, as long as you don't stray too far from this point, then the tangent plane and the surface won't be too far apart. If you go too far, that gap might get really big. But as long as you're close, this is the local linearization of the surface, the tangent plane. You need to know what the tangent plane looks like, because we're about to define what it means for a function of two variables to be differentiable at a point. Back in Calculus 1, the function was differentiable at a point if you had a well-defined tangent line. If you weren't quite smooth enough to have a unique tangent line, you didn't have a derivative. The tangent line has to be a good fit locally in order for the function to be differentiable. That was true in Calculus 1. That's going to be true in Calculus 3, except now it's not the tangent line that has to fit, it's the tangent plane that has to be a good approximation near the point x0. A function f of two variables x and y is differentiable at some point x0 if the function is equal to the tangent plane plus some error and here's the error part. There's some function epsilon 1 of x and y times the little change in x, plus another function epsilon 2 in xy times a little change in y. We'll think of this as a delta x and this as a delta y. We need these errors to go to zero fast. If the errors go to zero at a linear rate, that's not good enough. It has to go to zero at a rate faster than linear. We need the limit as delta x, delta y goes to 0, 0 of epsilon, I'll just say epsilon sub k of xy is 0. Both of these go to 0 in the limit as delta x and delta y go to 0. In this case, we have this going to 0, this also goes to 0, so the error terms go to 0 faster than a linear rate. So you see, if the function is differentiable at some point, then the tangent plane makes a good fit. We say that f is differentiable on a set S if f is differentiable for each x that lies within that set. We're going to show that f of x equals, let's say, x squared plus 2y is differentiable for all x not in R2. So this function should be differentiable everywhere. It is, after all, a polynomial. So let's see whether or not it is. We're supposed to have f of x equals f of x naught plus fx at x naught times delta x, which is x minus x naught, plus fy at x naught times delta y, plus epsilon 1 times delta x, plus epsilon 2 times delta y. So in other words, we have to have x squared plus 2y equals x naught squared plus 2y naught. fx is 2x, so it's 2x naught times x minus x naught, plus fy, which is 2, times y minus y naught, that's your delta y, plus epsilon 1 delta x plus epsilon 2 delta y. We need to solve this equation for epsilon 1 and epsilon 2. Now, you can see that we get, we're going to move all of the terms except for those involving epsilon 1 and epsilon 2 over to the other side of the equation. So, moving everyone over, we have epsilon 1 delta x plus epsilon 2 delta y equals, we'll have x squared, we'll have minus 2x naught x minus x naught squared, and we have also plus 2x naught squared. This will cancel with all but one of those. Plus, we have this 2y. We have minus 2y naught. That takes care of this. We have minus 2y and then plus 2y naught. So all of these cancel. We're left with x minus 2 x naught x plus x naught squared. That's x minus x naught squared. Now we need to make some matchings here on each side of this equation. If x minus x naught is delta x, we have delta x squared on the right-hand side. On the left, you can see that epsilon 1 is delta x, so that you get delta x times delta x. Also, epsilon 2 is identically 0, because there are no delta y terms over here at all. Also, note that in the limit, as delta x, delta y goes to 0, 0, epsilon 1, which is delta x, tends to 0. And then epsilon 2 also tends to 0 because it is identically 0. Therefore, f is differentiable at x naught y naught, but since x naught y naught is arbitrary, that means f is differentiable for all x naught that lie in R2. We've now defined what it means for a function in two variables, a surface, to be differentiable at some point. The tangent plane needs to make good contact. The errors involve epsilon 1 and epsilon 2 times respectively delta x and delta y. Delta x and delta y go to 0 at a linear rate. The epsilon 1 and epsilon 2 must also go to 0 so that the errors in the approximation by the tangent plane go to 0 at a faster than linear rate. That gives you good contact between the surface and the tangent plane. Good definitions lead to good theorems. We proved in Calculus 1 that if a function is differentiable at some point, then it is continuous at that point. Our definition of differentiability here in Calculus 3 will also imply continuity. If f is differentiable at x naught, then f is continuous at x naught. And of course, just like in Calculus 1, the converse of this theorem is false. What we'll do is very similar to the proof from Calculus 1. We'll take the limit as x goes to x naught of f of x minus f of x naught. Assuming differentiability, that's going to be the limit as both delta x and delta y go to 0 of fx at x naught delta x plus fy at x naught delta y plus epsilon 1 delta x plus epsilon 2 delta y. If x goes to x naught, then both delta x and delta y go to 0. All of these terms then, since this is a constant, all of these terms will go to 0. Both factors in this last two terms. We deduce then that the limit of f equals the function value. And that's what it means to be continuous. Nota bene in B stands for the Latin phrase nota bene, note well. The existence of the partial derivatives fx and fy does not imply differentiability or even continuity. Dun dun dun. Wow. These partial derivatives can exist, and yet the function may not even be continuous at the point in question. Let me give you an example. I want to give you something memorable. Here it is. The function is xy over x squared plus y squared when x and y is not at the origin, and 0 when x is at the origin. First, I want to show you that fx at the origin exists. We'll appeal to the definition of the partial derivative. Take the limit as h goes to 0 of f of 0 plus h comma 0 minus f of 0, which is 0, divided by h. If we're evaluating at y equals 0, we will get 0. I think you can see also the partial derivative of f with respect to y at the origin must also be 0 by symmetry. Now, I'm going to make the claim f is not even continuous at the origin. To see this, all I have to do is calculate two limits. Let r of t be the curve t0. We'll take the limit as t goes to 0 so that we're tending towards the origin. If we evaluate with y equal to 0 and x equal to t, we get 0. Next, suppose I take the 45-degree line towards the origin this time. We'll still take the limit as t goes to 0 so that we end up at the point 0, 0. But now we're going to have t squared over t squared plus t squared, which is 1/2. That's not equal to 0. We get different limits depending upon how we approach the origin, which means this function is not continuous. This function is not continuous at the origin. Also note that since it's not continuous at the origin, it can't be differentiable there either, because differentiability implies continuity. We've seen two very important examples today. Remember Clairaut's theorem? Provided nice things happen at that point in question and in a neighborhood, then the mixed second-order partials are equal. We saw an example where the mixed second-order partials were not equal, but in that case, the second-order partials were not continuous at the point in question. So it didn't violate Clairaut's theorem. Also, we've shown now that differentiability implies continuity, but we've seen a function now where both first-order partials, the partial with respect to x and the partial with respect to y, both exist, but the function is not even continuous, much less differentiable at the point in question. That's a very interesting issue. This raises an important question. What is required in order to have differentiability? Is there an easy test? The definition of differentiability for these functions of two variables seems a little awkward with this epsilon1 and the epsilon2. We demand a theorem. We must have a theorem, a silver bullet that tells us when we can expect these functions to be differentiable. Fortunately, there is such a theorem. It goes like this. If both fx and fy, if these exist and are continuous on an open set containing x naught, then f is differentiable at x naught. So you have to have some level of regularity for these first order partials on an open set containing the point in question. It's interesting here that the topology of the set ends up being essential to the truth of our conclusion, differentiability at this point x naught. For the proof, see advanced calculus. We're not going to prove this here. I thought that I'd show you some of the graphs of these important functions that we've had. Let's suppose that f maps x comma y into x times y divided by x squared plus y squared. So that's our function. And let's take a look at this. I'm using the plot3d command in Maple. I want to plot f of x comma y minus 1 to 1, y is minus 1 to 1, and I'm going to constrain the view to minus 1 to 1, minus 1 to 1, minus 1 to 1. I don't want it to stretch the axes, so I'm going to set scaling equal to constrained. Let's draw in the coordinate axes to this surface. And now you can see what's going on. Looks like we need to plot a few more points to get a better idea of what's going on near the origin. So I'm going to change this to be num points equals 10,000. We'll put the coordinate axes back. And you can see what's going on at the origin, that it's not continuous. As you approach the origin on the 45-degree line, you get one limit. As you approach on another line, you get a different limit altogether. So it's kind of like a weird crinkled napkin of sorts. The weird thing going on here as we get close to the axis, the z-axis, is happening just because we're dealing with a crummy approximate plotter that gets a little flaky near points of discontinuity. But the curve will actually go all the way in. It won't be defined at the origin. This function here isn't defined at the origin because the numerator is a polynomial of degree 2 and the denominator is also a polynomial of degree 2. By the way, terms that have both x and y, you add the powers on each to get the degree of the term. So degree 2 over degree 2, you expect something strange to happen as you approach the origin, and in fact, it does. We get different limits as we approach in different directions, as you can plainly see from the graph. What about that function that we dealt with earlier? It was x times y times x squared minus y squared all over x squared y squared. Now, that function should be
continuous. We proved that that function is continuous at the origin. The question was, what about the first order partials? Are they continuous at the origin? And how about those second order partials? It was really the second order partials that became the issue. Let me define the following. I'm going to define fx to be the derivative of f of x comma y with respect to x. And I should actually simplify that to make it look more like what we found. That's exactly what we had. We had a negative here distributed, so we had a positive x to the fourth, a minus y to the fourth, and a positive 4xy. That's the only difference. Let's also plot that. Plot 3D fx, x comma y. Let's go back and copy the plot information from the previous plot. Oops, we'll go back up here. In fact, we can just do plot fxy, fx. Now, you'll notice that we get continuity at the origin, but it looks like the next derivative will have discontinuities. Yeah, doesn't look like the next derivative will be continuous. So let's look at fy as well. Fy was the derivative with respect to y. That's what we had before, and if we come back here and now plot fy, we have the same kind of thing. It's the next partial doesn't look like it's going to be differentiable. Let's look at fyx. This is fyx. Let's go back to our plot and plot fyx. Now you can see we're having problems at the origin. Looks like we'll definitely have some discontinuities at the origin. Let's plot in the coordinate axes. And as you approach the origin from different directions, it looks like you'll get different values depending upon how you approach on various curves. Yeah. What about fxy? There you take the derivative with respect to x first, and then the derivative with respect to y. Let's plot fxy. We get this similar kind of thing, a curve that doesn't appear to be continuous at the origin. We have some problems at the origin. It might help if we backed out a little bit. You can maybe see what the curve looks like from a little bit bigger scale if we go from minus 10 to 10. Let's change all these to 10s. Oops. And one more. There, you can see this is a very crinkled surface, not continuous at the origin. It has kind of a big jump going on. Depending upon what direction you go towards the origin, you'll get different limits. So it turns out that these second order partials here are not continuous at the origin, and hence you don't get the equality that Clairaut's theorem would imply.